Thank you, sir. Thank you, Professor Sandeep Juneja, Professor Sandeep Trivedi, Professor Rama Govindarajan, and Professor Saravanan. Thank you for this opportunity and for this invitation. Yeah. So today I will talk about, because when the invitation came, I was asked if I can provide a survey of climate modeling in India. So I said it's going to be a very challenging job. And so I said I will focus on the IITM Earth System model and what are the, how it happened and what are our ongoing work priorities and future plans. And this is basically a teamwork, and I should acknowledge all the people, all my colleagues, Dr. Swapna, Sandeep, Rajesh, Ayantika, Manmeet Singh, Ramesh Vellur, and several other people who have contributed to this IITM Earth System model development. And without their support, I think this would not have been possible. I want to acknowledge that at the beginning. And Dr. Swapna is the main person leading the ESM development effort at IITM. With this, I begin. So when we talk about weather prediction and numerical weather prediction or climate prediction, when we talk, we have to keep in mind the scale of the phenomena, whether it's a weather phenomena or a climate phenomena, both in these space and time scales. Basically, when we are looking at the weather forecasting in the short and medium range, typically when we talk about it is up to 3 to 4 days, and medium range it goes up to something like 10 days. And this is basically dependent on your initial condition of the atmosphere. That is what is going to determine the skill of your predictions. That's the initial state of the atmosphere. So the initial observations are going to become important. And then when you go to the longer time scales, when you go into the seasonal time scales, like for example, the seasonal prediction of the monsoon or something, then we start seeing the influence of the ocean and also the land and different components of the Earth system. And when you go to climate change on very long time scales, we are talking about decadal variabilities and the effect of human influence, because human activities have also started altering climate. Then we have to have all the components of the Earth system, the atmosphere, ocean, and also the cryosphere, the land, biosphere, and also the human influence. Yeah, so that becomes basically a boundary forced problem. And so when we look at climate and weather prediction, this concept we have to keep in mind. And so as the scale increases, both in the space and the time, different components of the Earth system are going to become very important. That is the first point I thought I should convey. And this is a brief historical perspective. I think all the some of the speakers have already provided, but I thought I should just give an introduction to the NWP, numerical weather prediction. And the basic ideas were developed more than a century ago. And it was a Bjerknes, a Norwegian scientist in 1904. He proposed that weather prediction should be possible based on the well-established laws of physics. And he proposed it as a mostly deterministic problem. And so if we have sufficiently accurate knowledge of the atmospheric initial state, it should be possible to predict the future states. And later on during the First World War in 1922, Dr. Richardson, he attempted to solve these equations numerically by hand. And actually it was a failure, although his procedure was right, but I think it turned out to be a failure. And it was due to some other reason, because it was due to the problem of gravity waves, which was not aware at that point of time. His forecast actually failed, but that was an important lesson, learning lesson. And over the time, several obstacles had to be overcome. We had to understand a full understanding of the atmospheric dynamics. Later on, regular radio sondes made measurements of the atmosphere at different places, and also satellites, they provided the initial conditions. And also these stable finite difference schemes were developed, because these when you want to solve this numerical weather prediction, you need to solve it numerically. So finite difference schemes were developed. And so the ENIAC computer, yesterday Professor Saravanan mentioned, at the University of Pennsylvania. It came around the late 40s. And a major big breakthrough came by Jules Charny, von Neumann, and Fjordhoff, where in 1950 they integrated a simple what is known as a vorticity equation, barotropic vorticity equation. And this was a quasi-geostrophic approximation. This is something which we apply in the mid-latitudes and with a hydrostatic balance. And this basically eliminates the acoustic and gravity waves, but it retains the long planetary waves. And this was the first breakthrough, the numerical model of the atmosphere for prediction. And later, Rossby and team in 1950, they provide a first real-time successful weather forecast. And also subsequently, a general circulation model of the atmosphere is developed by Norman Phillips. And this is a numerical experiment. He could depict monthly and seasonal patterns of circulation in the troposphere. And I think this was the beginning of the general circulation models and climate models. And GFDL Princeton pioneered this thing, development of the climate model subsequently. And by 60s, Ed Lorenz had made an important discovery of the deterministic chaos. Using a very simple model of atmospheric convection, it's a three variable model, a nonlinear model with 3 equations and 3 variables. He showed that there are 2 regimes with chaotic transitions, although the equations are deterministic, but the transitions can be quite unpredictable. And so this transition can be very chaotic. So he proposed that even with perfect model and almost perfect initial conditions, the forecast loses all the skill in a finite interval of time. And so there is basically limits to predictability of weather. And this was a concept at that time. And of course, over a period of time, powerful electronic computers came. They provided a means of carrying the massive calculations. And recently, we are seeing massive increase in computing power. And so this is a brief summary. This was a slide from Professor Kamal Puri. And this is a brief summary of climate change, the science of climate change itself. So nearly 200 years back, Joseph Fourier, he had proposed the concept of a glass bowl effect, where these atmospheric concentrations of these gases like carbon dioxide can trap the long wave radiation from the Earth, and it maintains the warmth of the planet. And subsequent work by John Tyndall, it explains the basis of what we now call as the greenhouse effect. Basically proposed that the atmosphere admits the entrance of the solar heat, but checks its exit, and as a result, there's a tendency to accumulate heat at the surface of the planet. But I think the first quantitative estimate of the change in surface temperature to be expected from a doubling of CO2 came from Svante Arrhenius, a Swedish scientist. It was in 1896. He estimated this around 5-degree warming by doubling of the carbon dioxide. And later on in 1938, Guy Callender states that human activities have led to increased surface temperatures. And so the measurement of carbon dioxide, which is a very important gas, greenhouse gas, it started in the 50s by Charles Keeling, first at the Scripps Institute of Oceanography in San Diego, and later on it was moved to Mauna Loa in Hawaii. And now we have long enough measurements of these greenhouse gas concentrations, not only carbon dioxide, methane, and other gases. And yesterday, Professor Saravanan talked about this. And so the carbon dioxide has been steadily increasing, which we have seen. And a pioneering work by Manabe and Stickler and Manabe and Weatherall, these were landmark contributions, big breakthroughs. Because in 1964, they had this one-dimensional model of a convective adjustment, how to do both the radiative and convective adjustment to compute the thermal equilibrium of the atmosphere. And later on, Manabe and Weatherall, they used the concept of a fixed relative humidity. And this was a very important assumption. And they proposed that if we double the carbon dioxide in the atmosphere, it has the effect of increasing the surface temperature by about 2.3 degrees. And this was a remarkable achievement, finding in 1967. for the atmosphere with realistic distribution of relative humidity, and by about 1.3 degree for a relative realistic distribution of absolute humidity. And this was the first clear demonstration of the water vapor feedback. So because water vapor itself being a greenhouse gas is going to amplify the warming. And this finding led to the Nobel Prize in Physics in 2021 for climate science by Professor Manabe, and also Klaus Hasselmann for his contributions in the detection and attribution of human-induced warming. And so this is a I thought I should share this slide of Professor Manabe with his colleague Joseph Smagaransky, who was the first director at the GFDL Princeton. And this is the most, and this is by Piers Foster, the most influential climate science paper of all time. And this was yesterday also, it came out in the talks that whereas the surface and the troposphere, while the temperature increases, there is a warming, the stratosphere actually cools due to the when the carbon dioxide is doubled. And so I was very fortunate. I had an opportunity to work with Professor Manabe when he was the director at the Frontier Research System for Global Change in the Global Modeling Group, Global Warming Group. And so a very, very inspiring person and a very kind person. And so I thought I should mention this. And so going to the physical principles governing flow in both in the atmosphere and the ocean, it goes back to the classical Navier-Stokes equation and the thermodynamic energy equations, the momentum equation. So proposed, we initially developed the classical equations by Isaac Newton's, and so we have the so normally what we call in the atmosphere, we have what is known as the primitive equation model. We have the equation of for the horizontal momentum. We also, because it's a rotating platform, we have the Earth rotating about its axis. We have to introduce the effect of the Coriolis force. That's a new, and also we have the effects of the dissipation, momentum dissipation. And the thermodynamic energy equation, this is the first law of thermodynamics. On the right hand side, you will see a term Q, which is basically the heating. This is the coming due to all the heating due to the latent heating, the radiative heating, and also the sensible heating, exchange of the different forms of heat. So that is important. We have to keep that in mind. And we also have a mass conservation equation. And typically we assume the atmosphere to be in a hydrostatic balance for very large scale motions. But when it comes to very small scale like thunderstorm or something, so the hydrostatic assumption may not be valid. And this is the mass. So we have the mass continuity and the hydrostatic equilibrium. So the hydrostatic equilibrium, for example, if you have a non-hydrostatic atmosphere like a thunderstorm type of, it may not be possible. But in a large scale atmosphere, these are still very valuable approximations. And we have the water vapor mass continuity equation. This is a very important, because water vapor, it's going to change its phase from rain or ice or the different phases of the water vapor. And this is the change in the water vapor is related also to the dynamics, how water vapor is transported, how it converges. And because the condensation of water vapor also releases huge amount of latent heating. So it is intimately tied to the thermodynamic energy equation. And then these can in turn affect your divergence pattern, the flow patterns, especially convergence and divergence center through the vertical velocity. And so all these equations are coupled to each other and in a nonlinear way, and solving them always becomes difficult. We have to resort to numerical methods. And so when we look at this Q dot, the heating term and the moisture term and also the frictional terms, they are very harmless looking term, but the real problem is dealing with these terms. And so normally these are subgrid scale processes happening within the scale of a grid. And currently this is a slide that I took how to represent these processes. For example, it could be convection, shallow convection, deep convection, clouds, even the long wave radiation, short wave radiation, exchange of different fluxes from the surface, and the orographic drag. And these are all subgrid scale processes, and they have to be described in terms of the large scale variables, in terms of the mass, momentum, and heat transfers. And this we call them as parameterizations. So all the weather prediction, climate prediction models, most of them, they rely on the parameterizations to resolve these physical processes. And so basically what we have is for the basis of weather and climate models, we have the equations of motion, the laws of thermodynamics to predict the change in temperature, pressure, velocities, humidity, etc. And so when we start discretizing them, describing them in grid points on a sphere, so we can have millions of equations, tens of millions of equations to be solved at different levels, and we have different vertical levels, and the number of variables are also, it depends how many we want to include. So the computation becomes very, very enormous, and the time step is typically these are about 10 minutes. We march in time. And also the models have, with time, they have progressed in terms of resolution. In the 1990s, the horizontal resolution was something around 270 kilometers. These are the NWP models. Now, present day, even they are less than 50 kilometers. Some of the highest resolution weather prediction model in India is a global model at 12.5 kilometers for short range weather prediction. And so the enormous computations, and in the vertical, we have about in the present models, we are having about 64 vertical levels in the GFS. So the computations have enormously increased, and this we have to keep in mind. So one of the ways to solve these equations is through the finite difference method. But in the 70s, later, actually, the problems that there are other methods known as the spectral method, which I thought I should emphasize, because the model I will be briefly describing is a spectral model. So in a grid point model, normally all the atmospheric dynamics, atmospheric variables in space and time are solved on a finite difference grid. But in a spectral model, the atmospheric fields over the globe are represented in the form of waves using spherical harmonics. And spectral technique comes under the class of what is known as the Galerkin methods, and is very useful for solving numerically solving linear and nonlinear partial differential equations. And initial work started on the spherical harmonics even in the 50s, goes back to the earlier works of Silberman and later Platzmann in the 50s and 60s. But this, what they found was they applied it for simple non-divergent vorticity equation on a spherical domain. And this involved the computation of the nonlinear advection term. It required a lot of memory. It involved computation of in 4 integrals, not a double integrals, four integrals, and enormous memory allocations were required. So it was a kind of undesirable proposition at the time. And but people still pursued that even in the 60s and 70s. But the big breakthrough came in 70s by Eliasson and Orszag. But they developed a method known as the transform method for evaluating the nonlinear terms. And this became very, very popular, the transform method, and this popularized the spectral method. And later on, this was adopted for numerical weather prediction at operational and research centers. The William Burke and team from Australia, they developed the first global model, spectral model, in 1972, 74, 77. Later on, it spread to other places, and also NCEP and also the European Center and the National Center for Weather Prediction at US. So they started adopting the global spectral model technique. Basically, this is where the variables are explained. For example, a variable like, let us say, velocity, zonal wind speed, as a function of longitude, latitude, and vertical, and also in time, they are expressed in terms of the spherical harmonics. Where in the zonal, in the east-west, we call it as the zonal direction. It is represented as waves, sine and cosine waves. And in the meridional direction, in the latitudinal direction, it is expressed as the associated Legendre polynomials, PLM. And this is truncated with a zonal wave number of J. J is the zonal wave number. And it turns out that the solution of this is very useful because the spherical harmonics are the solutions of the Laplace equation on a sphere. And so the Laplace equation, once you cast it on a sphere, so these are the natural solutions, these spherical harmonics. And so this became a very popular method. I will not get into the details. And the first method, so William Booth, this was in 1972, he developed an efficient method for solving the vorticity equation on a single level using the spectral method. Later on in 1974, there was a multi-level spectral model was proposed with 5-level model. And later on, there was a more comprehensive model for simulation of the general circulation in 1978. Also, Kamal Puri, he contributed to this. Basically, you can see all the equations, the momentum equation, the thermodynamic energy equation. This is the surface pressure equation, which also integrates the mass conservation equation, and this is the hydrostatic equation. And in the vertical coordinate is normally is taken as the sigma coordinate, where it is the ratio of the pressure to the surface pressure. This was proposed by Norman Phillips, this coordinate system. And what they did in the spectral method was to cast, instead of writing the momentum equations in terms of the zonal and meridional velocities, they cast this in the form of the vorticity equation and the divergence equation, which are represented in terms of the scalars, the stream function and the velocity potential. So you can express them as Laplacians. So it becomes much more easy. And also, instead of having the velocity u and v, normally they take as u cos phi and v sin phi, where phi is the latitude. So this eliminates the problem of singularity at poles. So these are called the pseudo scalars, the capital U and capital V. And also because of the transform technique, availability of the Orzak's transform, all the nonlinear terms where they came out with a method to compute the nonlinear terms at the grid point and then transform them back to the spectral space. So this going back and forth between the grid and grid space and the spectral space became possible because of the transform method. And this became very popular subsequently. So the advantages of the spectral method is that there's an accurate evaluation of the nonlinear advection term, and it has very nice conservation properties, like you can conserve the mean square kinetic energy and the mean square vorticity, what is known as the entropy. It is conserved, and ease of modeling the flow over the entire globe becomes much more easier compared to the finite difference model. And also, one of the problems with finite difference is the problem near the poles. Because of the constant longitudinal increments, they yield small geographical east-west distances between grid points. And this can be a problem for the CFL criteria, which Professor Saravanan was describing yesterday. But the spectral technique is free from polar singularities. And also you can implement this, what is known as a semi-implicit time integration scheme, how to march in time. So the semi-implicit time integration scheme is a very stable scheme. And this becomes very easy to implement in the spectral method. And also the number of computations in the grid point compared to the grid point at the same resolution, they are fewer when you talk about a spectral model, and accurate and stable numerics. But there are also some disadvantages which can be overcome. For example, the Gibbs phenomena. Usually when we apply the spectral method, if there are sudden discontinuities, there can be spurious oscillations near the discontinuities of function. And of course, now through the use of filters, the Gibbs oscillations can be mitigated. Also, we can get unphysical spurious negative mixing ratios. For example, water vapor. This can be a problematic, and this can arise due to finite truncation. So we have to apply corrections to this, and have to be careful how to deal with this but there are ways to handle these issues. And so normally for the spectral, there are different two types of truncation. One is known as the rhomboidal truncation in the spectral domain. So the M is the zonal wave number, which goes from -j to +j. J is how many waves we want to have zonal in the east-west direction. And in the meridional, for the rhomboidal truncation, the meridional wave number L goes from modulus M to modulus M plus J. So this is known as the rhomboidal truncation, and this has more number of computations compared to the other truncation is known as the triangular truncation, where M goes like before -j to +j, but L is going from modulus M to J. So there are fewer computations, and also we have to make sure that the number of grid points, there is a consistency between the number of waves to be resolved and the number of grid points. Suppose we have n waves in the Fourier space, we need to have 2n plus 1 grid points to avoid aliasing. And also for the FFT, so normally in the zonal direction, we do the fast Fourier transform computations. So the number of grid points have to be usually a function of 2 to the power of 2, and the number of grid points are typically for a triangular truncation. If we have n waves, for example, T42, if we have 42 waves, the number of grid points in zonal direction has to be should be 3n plus 1, and it should also be a power of 2. So normally we take about 128 points, which is 2 power 7. And also the number of, for the Legendre transform in the meridional direction, we need to have 3n plus 1, 2 by 2 grid points in the triangular space, in the triangular truncation. And for the rhomboidal truncation, it is 5n plus 1 by 2. So these are things that we need to take care. And this is just a table I thought for the different resolutions, both for the different wave number truncations, R7, R for the rhomboidal and for the triangular, how many grid points we have typically in the zonal direction and meridional direction, and how many spectral coefficients. And I have specifically marked two. One is the T62, which is what we are using in our model for the Earth system model. It has 62 waves in the zonal direction, and we have number of Gaussian latitudes in the north-south direction. We have 94, and in the zonal direction we have about 192 points, typically about 2.5 degree resolution. And so the first version of the IITM ESM was based on a triangular truncation of T126, which had a higher number of grid points both in the latitude and longitude direction. This is just for the information. And so the idea is the climate. We have to keep in mind that consider when we started, much of the work in the West had already been taken, had already occurred, and Manabe's, this is the pioneering work, first climate model, the atmospheric circulation model, where we could also include the effect of soil moisture in the model. We could study the hydrological processes, and this was in 1969. So this was developed for the Atlantic Ocean, basically where you have the land and the sea separating, and they had it extended from the South Pole to the North Pole, and they could compute this, make this atmospheric circulation calculations and how heat was transported in the atmosphere. So, and how the precipitation and evaporation changes occur across the latitudes. So this was in 1979. And subsequently, the climate model with the coupled model, the first coupled model, again, Manabe and Kirk Bryan. Kirk Bryan was the oceanographer who developed the first MOM. In fact, it goes back to Kirk Bryan's original work. So they could couple an atmosphere and the ocean model, again for the Atlantic Ocean. And so they could not only look at the changes in the atmospheric heat transport, but also in the ocean, and how it affects how the oceanic heat transport can affect the polar ice pack. So this was more than 50 years ago, back in time, and so this was a very important contribution. And they first demonstrated the most interesting result of the calculation is a quantitative demonstration of the effect of ocean currents on the distribution of temperature, relative humidity, and precipitation pattern. This is done by comparing the state which is obtained from the time integration of the atmosphere model. That is the first stage with the state which is obtained from that of a joint ocean atmosphere model. So significant progress had already happened there. And this was a paper in 1975 by Manabe and Weatherall, where they used the first work was with 1967 with simple one-dimensional radiative convective model. But now they had a three-dimensional model where they could model the effect of the impact of the CO2 on what happens to the surface temperature change, and also what happens to the temperature pattern in the atmosphere. So with the doubling of the carbon dioxide, you can see the warming of the troposphere and also the cooling of the stratosphere. And subsequently by the 80s, they had, this is again from Manabe and Stauffer, they had a fully coupled model for the entire globe, how to develop this atmosphere and how to couple the ocean and atmosphere model, how to exchange from the ocean, how to provide the evaporation, which is the source of the evaporation, this sensible heat for the atmosphere. And in turn, the winds, they provide the surface stress and affect the ocean currents. And so due to the changes in the ocean thermodynamics, and so we have changes in the temperature and the salinity and the sea ice. So they had developed this procedure of coupling both the atmosphere and the ocean. And so which is important for studying the fluxes, exchange of fluxes of water, heat, and momentum. And so when we are going to climate, as I said, we need to look at the not just the atmosphere, it goes beyond the atmosphere and the ocean. We have to also start looking at the effects of the glaciers, for instance, and also the changes in the atmospheric concentration of all the atmospheric composition, and also the effect of hydrological processes at the surface, and also the effect of ocean biogeochemistry, like changes in the planktons, changes in the chlorophyll, and changes in the ocean nutrients. So the ESMs are very powerful tools. They provide information about the physical, chemical, and biological mechanisms governing the rates of change of elements of the Earth system. So, and these are very important for understanding long-term climate, and also the effect of air pollution and natural forcings like the volcanoes. I will come to that. So how it all started at CCCR, at the Center for Climate Change Research in IITM. And so in India, basically the atmospheric models, people had worked even in the 70s, 80s, and 90s on atmospheric models, and also on standalone ocean models at different places, at IITM, at PRL, at Indian Institute of Science, at IIT Delhi, at several places, mostly in standalone mode. And the studies were mostly focused on monsoon, what is some kind of sensitivity experiments, both from the weather point and also from climate point, and focusing on the monsoon seasonal forecasting. This was mostly the status in the 70s, 80s, 90s, even in the early 2000s. And I think IAC had developed a coupled model, not developed a coupled model, they had ported the coupled model, the CSM on a parallel computer, if I remember, and they had made the 100-year run from IAC. But coupled modeling didn't, I mean, virtually it was hardly existed in India. This is even in the early 2000. And so when we wanted, so the Center for Climate Change Research from the Ministry of Earth Sciences, it started in 2009. And one of the mandate was to develop an Earth system model. And honestly speaking, we are not sure how we will be doing this at that time. And 2010, when we started, so our goal is to, plans where we have to have an Earth system model from India for long-term climate studies and participate in the CMIP 6 experiment, because At that time, the CMIP 5 was already in progress, and the IPCC, that it was all almost coming to a CMIP 5 experiments were almost coming to an end. And the IPCC report came out in 2013. And by 2010, it was very difficult. We had already missed the boat. And we said that, okay, at least let us aim for CMIP 6. That was one of the, in a simplistic way, we started. And also contribute to the Intergovernmental Panel on Climate Change. So this was our initial thinking, and basically the coupled model intercomparison project phase 6. These are standard experiments. This project is under the WCRP, the World Climate Research Program, one of the projects of the key projects of the World Climate Research Program. So they come out with the standard protocols of what experiments we should be doing to understand the science of climate, various climate science issues, topics, and also it also provides the basis. The outputs from the CMIP 6 models are used for the IPCC assessments. And so participating in this important project is a very key step. So they have in the CMIP 6, there is a main experiment known as the DEC experiment. So all the groups, all the participant groups have to they have to contribute to the DEC experiment. That is one of the commitments. And there are other experiments, dedicated experiments known as the model intercomparison experiment. It could be on carbon cycle, it could be on land use, paleoclimate, forcings, atmospheric chemistry, clouds, radiation, scenarios. So these are all the MIP experiments, and also the regional climate geoengineering. So we have the option to select which, if in case we want to participate in the MIPS, model intercomparison programs. But the DEC experiment is a kind of a compulsory experiment that all the contributing models have to do this standardized experiment. So the protocols, the modeling experiments are all standard. We all do the same experiment, but with different models. And then it becomes a standard basis for evaluating the models. It's a kind of benchmark type of experiment. So IITM agreed, we committed, because we were still not very confident at that time, but we decided that, okay, we will go with the DEC, and maybe one or two, we took a kind of conservative approach, maybe one or two MIP experiments if possible, but our model itself was not ready at the time. And and now the ambition is, now these are some of the very powerful statements coming from the 6th assessment report, that there's a very strong attribution. Human influence has warmed the climate at a rate that is unprecedented in the last 2000 years. And in fact, you can see this very steep increase in the temperatures coinciding with the increase of the greenhouse gases, especially the carbon dioxide. And presently, the warming, the global mean temperature 2021 is at the end of 20 is 1.21 degrees. And 2021 happens to be the 6th warmest year on record, despite having a La Nina, a persistent La Nina conditions in the Pacific last year, which maintained cooler temperatures in the Central and Eastern Pacific. The mean temperature was about 1.21. So climate change is there, it is already happening. And also this said that this is the warmest multi-century period in the last 100,000 years. And so this warming is unprecedented. And when we also look at the change in the observed temperatures and what is simulated by the models, all the CMIP 6 models, which include both the human influence and the natural forcing, and the green line is only the natural forcing. Much of the increase in the warming trend can be explained only when you have the human influence. Otherwise, we cannot explain this observed warming trend. And there are also episodes like there are periods where there was a cooling in the global mean temperature. This is the Pinatubo eruption in the 1990s, and also we see this is which we also see in the natural forcing run, and also in the this is all from the CMIP 6 models, and this is the human all forcing run, human and natural. We can see the cooling episodes associated with the volcanoes. So except for this episodic cooling due to the volcanoes and maybe solar irradiance changes, the 11-year cycle, the overall warming is mainly attributable to the human influence that came out. So how to do? So we wanted to be in a position to contribute to these type of, from IITM to these type of experiments, and also make the future projections. In the AR6, we have it says that global surface temperature will continue to increase until the mid-century under all the emission scenarios. And global warming of 1.5 degree and 2 degree will be exceeded during the 21st century unless deep reductions in carbon dioxide and other greenhouse gas emissions occur in the coming decades. So in fact, the 1.5 degree will be crossed in the next 20 years. That is what all the models are indicating, even in the very low emission scenarios. And the SSP 2.245, which is kind of the middle of the road scenario, socioeconomic pathway scenario, we will still cross the 2 degree limit, what was agreed in the Paris Agreement. That we will be crossing even in the SSP 245. And the high emission scenarios will be far close to 4 and close to 5 degree. This is from the multi-model mean, but there are some models which show even higher range in these in these projections. So this is a big concern. The future is, we are expecting that temperatures will get warmer, and the IITM model has also contributed to these projections. And it's not just the temperature and surface, also the oceanic. So we can see this warming not only at the global scale, even over the land and the ocean and the near surface air temperatures. This is a very important indicator. In addition to that, we can see the warming, the attribution of the warming across different continents coming from can be explained only through the human influence, which is coming out. And precipitation, the other important thing we are seeing is precipitation changes mostly in the since the mid 20th century. There has been an increase in the precipitation, global precipitation. And the models are indicating that, and mostly in the high latitudes, between 60 to 90 degrees. And this precipitation increase is strongly linked to there's attribution due to the human influence, due to the warming, due to the global warming. And the decline of the Arctic ice, this is very pronounced. You see a very strong decrease, especially, and the decrease has been pronounced after 2000. And the models are indicating that this is due to the influence of human. The Antarctic is a much more complex change in the Antarctic sea ice. Antarctic sea ice was little more stable, but the models, although they indicate a decline, the projected decrease, there are uncertainties in the models with respect to the Antarctic. And yesterday, Professor JS was nicely mentioning about the Antarctic sea ice changes, which are linked to circulation changes in the ocean. And since 2016, we are also seeing that there has been a decrease since 2000, even in Antarctica. And so the ocean warming dominates the energy inventory, accounting for 90, much of the heat is being taken up by the ocean. Nearly 91% of the observed energy increase for the period 1971 to 2018. You can see that and much of the warming we see in the first 700 meters of the ocean in the subsurface. And when we go to even deeper levels, there is a strong increase in the ocean heat content. And you can see these are the heat content, what are the trends in the observed ocean heat content, spatial map from 1971 to 2014. You can see strong increase in the 0 to 700 meter, but there are some variations when you go to deeper depth. These are associated with circulation changes in the deeper levels. And it also has, due to the expansion, thermal expansion of the ocean, and also melting of the glaciers and the land ice. So these contribute to increase in the sea level. And so the observed sea level increase budget, we are able to explain the contributions due to the thermal expansion, and also the mass addition from the ice sheet and the glaciers. And this is all coming out very clearly. And the same thing, so combining the attributable contributions from glaciers, ice sheet, surface mass balance, and thermal expansion, it is very likely that human influence was the main driver of the observed global mean sea level rise since at least 1970. And Dr. Swapna will be, I'm sure she'll be talking about this in the afternoon and tomorrow. And also the IPCC assessment showed that there's a very strong regional attribution. So with every increment of global warming, changes get larger in the mean temperature, precipitation, and soil moisture. So this is the observed change presently at 1 degree. And this is what we simulated by all the CMIP6 models. Models are able to pretty much capture the pronounced warming in the middle and high latitudes. And so with at a 1.5 degree warming level, this pattern emerges out much more prominently, and more prominently at the 2 degrees and 4 degree warmings. And the associated precipitation changes, we see strong increase in the precipitation in the middle and high latitudes. The monsoon regions of the West Africa, South Asia, we see an increase because of the increase in the water vapor. Because with every 1 degree warming, the water vapor increases by 7%. So due to the winds which transport the water, and also due to the convergence of the water vapor, strong convergence, we get more precipitation. So monsoon precipitation over South Asia is projected to increase in the future. And these areas where there's a decrease in the precipitation, these are mostly the subtropical areas which are associated with the descending branch of the Walker-Hadley circulation. And that is where the drying. So we see pronounced drying over the Mediterranean and parts of extreme West Africa, and also over the Southwest Australia and in Southern Africa and South American region. So the subtropical areas are projected to get drier. So it's like a wet gets wetter and the dry gets drier paradigm. So this is a very typical signature of the intensification of the hydrological cycle. So the hydrological cycle is projected to intensify with global warming. But we have also to keep in mind that apart from GHG, there are other drivers, anthropogenic drivers like aerosols. So this is the observed warming during the period 2010 to 2019 relative to 1850 to 1900. It's about 1.1 degree. And if we had only well-mixed greenhouse gases, the warming would have been about 1.5 degrees. So the effect of aerosols, mostly other human drivers, they have kind of compensated for this increased temperature by about 0.4 degrees. Mostly the sulfur dioxide emissions in the anthropogenic sulfur sulfates, and also to some extent nitrogen oxides. So we have to keep in mind that it is not only greenhouse gases, it is also aerosols are also becoming important. And also there are other carbonaceous aerosols like organic carbon and black carbon, which influence the temperature patterns. And also this has important implications for the hydrological cycle and monsoon. This I will quickly come. And this is a paper by Salim Bonfils et al. In detection attribution study based on the CMIP5 models, and it has been used in the IPCC in the water cycle chapter. So the typical fingerprint of greenhouse gas is a kind of warming everywhere globally, temperature fingerprint, which pronounced warming in the high and mid latitudes and polar regions, and and we see a corresponding increase in the precipitation, and also some of the tropical areas, monsoon areas. And whereas mostly the subtropical areas, we see kind of drying pattern associated with the descending Hadley cell. When we look at this fingerprint of aerosol, because aerosols are anthropogenic aerosols, mostly they have dominated the northern hemisphere from the continents of US and Europe and Asia. And so we get a kind of interhemispheric asymmetry, the cooling in the northern hemisphere relative to the southern hemisphere. And typically now studies are showing that if we cool one hemisphere relative to the other, this leads to a southward shift of the ITCZ. That's the area of maximum convergence and low pressure region, and convergence of winds from both the hemispheres. This is typically the ITCZ is associated with heavy cloud cover, and this ITCZ will shift to the south. This is a typical fingerprint of the aerosol forcing. And also there are attribution of the greenhouse gas and the aerosol on the aridity, that is basically the soil moisture changes, you can see that changes in the aerosol fingerprint have pronounced. They can lead to declines in the precipitation over India, over the monsoon regions of West Africa, and so on. And these are the typical fingerprints. So how did it all start? So when we started, we thought we should have a model to develop a model for detection, attribution, and projection of global change, and also regional monsoons. And we should also be able to capture the some of the teleconnections, because monsoon or India precipitation has links to other drivers like El Nino, Southern Oscillation, and other drivers. And those teleconnections have to be captured. So our roadmap was to start with a simple, because if we are going to start from scratch, we will not be able to meet the targets. So our idea was we start with an atmospheric ocean coupled model with realistic mean state. So the climatological mean state should be fairly realistic. It should have fidelity in capturing the global and monsoon climate. It should have a realistic representation of the interannual variability and features of ocean atmosphere coupled interaction. And once you have such a model, you can include various components of the Earth system model like biogeochemistry, interactive CIs, aerosol and chemistry transport. So this was our approach. And at that time, fortunately, there was a formal agreement between MOES, Ministry of Earth Science from the Government of India, and the NOAA in USA in 2011. And the plan was to implement the NCEP CFS, the coupled forecasting system, for seasonal prediction of the Indian monsoon. So this was the idea. So this was done at IITM Pune. We can have this model, NCEP CFS model for seasonal forecasting. And by the way, this coupled forecasting system CFS from NCEP was not really a model for climate, long-term climate studies. It was basically for the seasonal forecasting. It was a coupled model, and the atmospheric component, it is known as the GFS, a global forecast system, with the T126 triangular resolution, 110 kilometers, 64 vertical sigma coordinates, sigma levels, and the model top is 0.2 millibar. It has various physical processes. I'll not go into the detail. A simplified Arakawa-Schubert scheme, PBL processes, radiation, and land surface process, NOAA model. And also an interactive ocean model, the modular ocean model, MOM4, from Griffiths et al. And this is resolution half a degree poleward of 10 north to 10 south. And near the equator, it was a quarter degree between 10 south and 10 north, 40 vertical levels in the ocean, and interactive CIs. And so we said that we will take this model and why not use this model for developing the ESM. And this we took almost 3 years, and it was quite a bit of struggle. And I should thank this entire team led by Dr. Swapna, and she made a very important contribution. So when we were looking at the CFS model, we made a kind of a free run of the model starting from 2009, initial conditions. What we noticed was the global temperature in the first 20-30 years, it would drastically decrease. This is the global temperature, and then stabilize. So this problem is known as the climate drift. So this CFS model had a very strong climate drift, which we wanted to avoid. So in a very simplistic way, we thought that maybe why not replace because the ocean covers more than 70% of the globe, why not replace the MOM4 with a newer version? And that is how we went for the MOM4 P1. That was the model that went into the version 1, ESM V1. And interestingly, some of the physical processes in the MOM4 P1 are better. They have better treatment of how the solar radiation penetration happens, how the mixing happens. They are better represented in the MOM4 P1. We thought that why not take out MOM4 P0 and include P1. But that was a very hard job. It was not so straightforward. And so our colleagues have worked on it, and finally, it was possible to make this model run, a free run by changing, and this was a kind of in-house development mostly. And so we could make a free run for more than 100 years, and we reduced this bias, the drift, substantially by more than 0.8 degrees. I think this was a substantial, so that is the first time we saw some success. But it took quite some time to reach this stage. And so you can see that this is the global mean surface temperature, 2-meter temperature, how it decreases in the CFS V2, and the drift is reduced considerably in the MOM4 P1. And also we see this in the global mean SST, sea surface temperature, and also we see this in the tropical sea surface temperature. So this was the first success that we saw. And why does this happen? Then we looked at this paper by Delworth et al. This is from the GFDL group, and they had also a similar problem, why this drifting happens in the coupled models. So the climate models drift because many times due to some problems, biases in the models. So this is the global mean temperature. This is the difference in between the simulated and observed global mean ocean temperature as a function of depth and time. So along x-axis we have the time, in the y-axis we have the depth, and these are the differences between what is simulated and observed and how it changes. So as the model integration proceeds, we see that the subsurface ocean, even in the GFDL, this is the older versions, GFDL CM 2.0, and this was the CM 2.1. The deeper oceans tend to get warmer. The heat goes inside, whereas the surface starts cooling. This is a very typical problem. And the CFS model also is had the same problem, what we saw here with the MOM4 P0. And this was substantially mitigated with the MOM4 P1, that is the ESM 1 version 1. But the good aspect was it being a seasonal forecast model. The benefits we saw that was that some of the drivers of this intra-annual variability, like the El Nino Southern Oscillation, they were very realistically captured. In fact, even to some extent in the CFS V2, but it was substantially improved. This is the variance of the sea surface temperature, intra-annual variance of the sea surface temperature in the Pacific. So the pattern of SST variations in the Pacific are more realistic compared to the observation when we compare with observations as opposed to CFS V2. That is good news. And also we looked at the seasonal cycle of monsoon precipitation, and the monsoon precipitation has strong teleconnections with the El Nino Southern Oscillation. And normally whenever there is an El Nino in the Pacific, we mostly get a deficient monsoon over India. And the correlation between ENSO and monsoon peaks following the monsoon season. And these features were very nicely captured by the IITM ESM version 1, and also the seasonality of the Nino 3 SST variations. This was another good point. And we also did a wavelet power spectrum of the Pacific SST, the Nino 3.4 SST, to look at the different time scales. So the model, the ESM1 had a very nice ENSO signal, the 4-year periodicity. And also now they're talking about a decadal oscillation, which has a time scale of about 16 to 20 years. And this feature is also captured in the model, in the ISM even. So this model has got good teleconnections with the Pacific. But one major problem we still had was the ice in the model. I'll come to that. In the sea ice, both in the Arctic and Antarctic, in the version 1 was getting depleted. This was a major bias in the model. And also the radiation balance. To have a long-term clear model, we should have a radiatively balanced system. So at the top of the atmosphere, there should be a balance between the incoming and the outgoing radiation. So this is very, very important, because once we add more carbon dioxide into the atmosphere, we are introducing an energy imbalance, or make a change in the aerosol. We are including a radiation imbalance. So unless you have a radiatively balanced system, we will not be able to evaluate what is the effect of the radiation imbalance due to this anthropogenic forcing. And unfortunately, this CFS, the first version of the ESM model, had a huge radiation imbalance, even with the pre-industrial state, with the pre-industrial control run. And this was a serious limitation. And there were other biases like the sea ice in the Arctic was underestimated significantly, substantially. And so our concern was how to improve the radiation balance and how to improve the Arctic ice. This was our first priority. And so you can see this is the version 2. That is how from the version 1 to 2, this is the improvement. This is the radiation flux, the incoming solar radiation. You can see there's a there's a strong peak near the tropics, and the incoming radiation decreases as you go poleward. And the outgoing flux doesn't have, it's not so much of a bell shape. It's more or less uniform. It depends on mostly on the temperature of the surface. And so the net in the tropics, there is a net heat gain and energy input. This model, even the observations, it is very similar. So the model gets this basically kind of, the model should be able to capture this energy gradient between the tropics and the high latitudes. That is coming out very clearly. And we could also fix the radiation imbalance. I will come to that. Now, presently the model has the radiation imbalance of the top of the atmosphere at around 0.8. I will describe more about this. Okay. And this is the pre-industrial setup. And we could also, so the SST, the air temperature stabilized at around close to 14 degrees, the 2-meter air temperature, and the SST is at around close to 18 degrees. So this was after 500-year simulation. We also improved the simulation of the Arctic ice and compared, this is the observation is also shown by red. So we significantly improved the distribution of the Arctic ice in the version 2, ESM2. And how did this happen? And the version 2 basically is in fact a lower resolution because we had to do a lot of testing. And so T126 was not a good option because every time you make a test run, it takes time. You have to run the model for 50, 100 years. Then you find out what is the bias, how to rectify that, go back. So it is very time consuming. So on purpose, we brought down the resolution to T62, 64 levels. And we also include aerosols. I will come to this in my part. And we have this modular ocean model. We have a 1 degree poleward of 10 degree north, and near the equator about 0.33 degrees. We have 50 vertical levels now. We change 50 vertical levels in the ocean. It has an interactive ocean biogeochemistry and also a sea ice simulator. So this was the version V2. And yeah, the reason, as I said, in the version 1, we had an energy imbalance of about 6.6 watts per meter square. This is clearly not acceptable. And the surface, it was about 1.2. So there was a difference between the surface and top of the atmosphere, about 5.4 watts per meter square. This was clearly undesirable. And because totally right now we have added something like more than 3 watts of energy due to the human activities. So with the pre-industrial setup, an imbalance of 6.6 is undesirable. So we wanted to bring this down. Much of our effort to get a radiatively balanced. Presently, we have managed to get it something around 0.8 at the top of the atmosphere.
Dr. Krishnan, can you hear me?
Yes, yes. Yeah, I can. Yes, Professor Juneja. Hello?
You can hear me now?
Yes, I can.
I have a small request. This is enormously interesting, so we'd like you to continue, but we've scheduled this other speaker right after you. So
okay.
Maybe if you can, if you wish, you can wrap up in the next 5 minutes or so, and then we can meet again at 4 p.m. and have a follow-up discussion with everybody. Would that be all right with you?
Okay. Yeah, fine. I will try to wind up as much as possible. Yeah, fine.
If you want to again take much more time at 4 p.m., that's perfectly fine.
Yeah, I have 5 minutes will be difficult, but maybe I will quickly go to the last slides.
Sure.
Yeah. Yeah. So
very sorry about this, but
yeah,
have you continue, but somehow the schedule is set.
Yeah. So yeah, basically I will go to the last what. Yeah, so basically what we have is from the version 1, we had significantly reduced the bias in the global mean SST. Now with the version 2, we have reduced the radiation imbalance. It has an improved representation of the mean monsoon through a new convection scheme that has gone. And also it has a very realistic depiction of the Indian Ocean dipole and teleconnection with the monsoon. We have added time varying aerosols. I didn't touch. And we have also included the effects of volcanic forcing. And we have improved the Atlantic meridional overturning circulation Our Arctic sea ice has improved in this model. It has an interactive biogeochemistry. And also we have included the hydrological balance through discharge of runoff from land to ocean. And this model contributed to the CMIP 6 and IPCC-CR6 and National Climate Change Report. This is the quick summary. The ongoing and so in the future, our plan is to develop actually it has already started, a 27-kilometer resolution atmospheric version for dynamic downscaling. So this will be just an atmospheric component of the IITM ESM. And we are thinking this is the next, already this work is in progress. We'll complete it in the next couple of years. We also want to add a new dynamical core known as the triangular cubic octahedral grid. And this is also in progress. And we want to add ice sheets. And this work has also been started is in progress. Interactive aerosols and atmospheric chemistry. So right now the aerosols that are given in the model are based, they are developed for the CMIP 6. They're kind of all the optical properties of the aerosols are prescribed, like the aerosol optical depth, single scattering albedo, asymmetry parameter. So these are given as fields, they're prescribed, and then the optical properties, they interact with the radiation code in the model and produce the changes. And we also are thinking of including a carbon cycle. Eventually, we are thinking to have a community Indian Earth system model. We want to have our own model, community model from India. We are targeting this CIESM from 2020-25 and participation in CMIP 6. And this is the T574. This is the 27-kilometer version of the IITM ESM. For downscaling, we'll be doing it global. So because of the improved precipitation, there are improvements in the monsoon precipitation, but it's particularly useful for studying extremes, precipitation extremes, and also cyclones, and also the land sea ice simulator, which I think Dr. Swapna will be talking. And this is the triangular cubic octahedral grid that we'll be going to. And this is very good, especially it provides higher resolution in the tropics and also can be parallelized more efficiently at lower cost. This work is also in progress. So with this, I want to come to my end of my talk. Thanks for your kind attention. I'm sorry it took quite some time.
No, we should apologize. It would be great to have a longer discussion. I think there are a lot of questions also that people have. So we can offline coordinate to see whether it's in the panel discussion when we meet next tomorrow, or if today you have some time that we can just do offline.
Yeah, I can do offline. Maybe whenever it's suitable, I can present the rest of what I wanted to say.
No, so very sorry, Dr. Krishnan, if there's some fault from.
No, I'm sorry. I think probably I should have. No. Kept it. Shall I stop my screen? Stop sharing the screen.
Okay. Would you have the time at 4 o'clock? We have the whole afternoon session there just for discussion, and you could just even take an hour if you like, because it would be very, very helpful. And panel discussion, there'll only be little time and everyone will be speaking. So
yeah,
sorry, you could come at 4 o'clock.
Yeah. Okay, Professor. Yeah. So maybe 4 o'clock I'll join. I'm really sorry. Maybe the limit slides I should have restricted. But I was worried what to talk, and maybe I included too many of them.
Actually, it has been fantastic. It is a fantastic and very pedagogical, walk through the whole development of this model we are so proud of. So thank you very, very much. And only thing is, if you can come back at 4 o'clock, I know it's
Sure. I'll do that. Yeah.
Then please go at the same rate from where we hurried you. And
yes. Yeah, no problem. Sir.
Thank you very, very much. And we take all the discussion at that time also.
Yes. Yeah. Thank you, Professor.
Thank you very much.
Thank you very much.